What I wanted to do here was what I call my waves intro, and this is where I just want to talk a little bit about what you will have learned in level 1 if you did it. If you didn't, well, this is a good time to have a quick look at it. Waves, I think the first type of wave you're probably familiar with. Waves sort of at a beach, got troughs, you got crests. Waves are all about transfer of energy. So there's a disturbance here, and after a certain time period, the disturbance is felt here. It's a transfer of energy. Now the medium through which it travels has properties, and with waves traveling through the air, the particles, so at any point when a sound wave travels, the particles vibrate backwards and forwards in the direction of travel of the wave. This is called a longitudinal wave. Whereas a wave, and this is not a good way to actually draw a longitudinal wave, because a longitudinal wave, like I said, the particles are moving backwards and forwards. So if this was a sound wave, you got the particles all in there, and then they get further apart, then they get closer together. This is all based on the assumption that time has stopped. So a longitudinal wave, like a sound wave, is a series of compressions and rarefactions, areas where the pressure has decreased. So this is all about pressure, the transfer of waves. And it all moves very, very fast. These compressions move very fast, but the actual molecules just move backwards and forwards like this. But the compression moves very fast, in fact, at the speed of sound, which in air is about 330 meters per second. Those are longitudinal waves, but they're often displayed like this, because electrically they can vibrate a speaker that can be converted into a voltage, which is displayed like this. So the actual wavelength in a sound wave is this distance here. On the actual graph that we use, the wavelength is from there to there. It's from one peak, if you like, to the next peak, or in this case, from that part, you've got a positive part, then it goes back to zero, a negative part back to zero. That's a full wavelength. So this would be half a wavelength. When we look at waves like this, so don't get confused. The sound wave is often displayed like that electrically, but it actually exists like that. The display of a wave like this, where I said that this is the wavelength, that's our symbol for wavelength, lambda. This is called amplitude. It's to do with the intensity of the wave. The more intense, the bigger that is. Doesn't change the wavelength. Now there's something called frequency. Frequency is if you were to stand at one place and let the wave travel past at the speed of whatever it's doing, speed of sound, the number of waves that would pass in 1 second is the frequency. So it's the number of waves generated or passing a point per second. So if the wavelength is this long and this many pass a point in a second, then it will do frequency times wavelength distance in 1 second. So we can call that velocity because it was distance in 1 second. So that is our wave formula that we use all the time. Now there are transverse waves. Now transverse wave is where the amplitude, or as the wave travels, so as the wave travels through, the particles are vibrating up and down. So you've got these particles, if you like, and they vibrate up and down as the wave travels that way. So that in a transverse wave, the particles vibrate at right angles or perpendicular to the direction of the wave travel. So that's why we call it transverse. So this type of representation of the wave, to me, is more representative of a transverse wave than a longitudinal, but you'll see both done that way. What waves are transverse? Surface water waves are transverse. Now, we often use slinkies, and you can sort of flick a slinky like that, and you get a transverse wave, or you can sort of, you know how a slinky goes like that? You can sort of push it that way, and the pulse runs down that way. So slinkies are great for showing both longitudinal and transverse waves. Sound waves were longitudinal, and surface water waves are transverse. But then we come to this special category called electromagnetic. Now, electromagnetic waves, or EM, the electromagnetic waves, these are pictorially described as transverse, but what are we looking at? So if that goes out at right angles to the black one, we could say that this is the electric field, and the red one is the magnetic field. And they travel, so the intensity of the electric field and magnetic field is perpendicular, or the direction is perpendicular to the direction of travel. So we call that a transverse wave, right? But nothing's actually moving. The light travels in a straight line. It's just that if you could stop time and measure the intensity of the electric field right now at, say, that point, if we could stop time, then we'd have quite an intense negative electric field. Okay, a short time later, it would be zero as this bit moved to here. So electromagnetic waves have this electric and magnetic intensity, which is varying as it travels through space. And they travel through a vacuum. So really what they're actually, the medium is space, is the magnetic and electrical properties of space. So this is what light is. This is what infrared is, microwaves, radio. So it's only visible light that we actually see. Ultraviolet we don't. We've got X-rays and gamma rays. What changes on all these is the wavelength. Visible light is about this distance here, would be half a micrometer, or 1/2000th of a millimeter. Whereas a radio wave can be 100 meters long in its wavelength. And a microwave in your oven can be 10 centimeters long. And an X-ray can be like a billionth of a meter in terms of its length. So the shorter the wavelength, the bigger the frequency, because they all travel. If this is our wavelength formula, V equals wavelength times frequency. With light, it's C equals wavelength frequency. They all travel at the speed of light, which is 3 times 10 to the 8 meters per second. And that means if the wavelength gets smaller and smaller, then the frequency gets bigger and bigger. But there's something else about these waves. As the wavelength gets smaller and smaller, the energy gets much bigger and bigger, which is why X-rays and gamma rays can damage our DNA. So that's a brief introduction into waves.